Picture this. It's 3 a.m. Your pager is absolutely screaming. You stumble out of bed, crack open your laptop, and pull up your global monitoring dashboard. And everything is a perfect, vibrant green. Your CPU utilization is barely at 40%, memory is completely stable. Your HTTP error rate is sitting at a flat 0. You're just about to close your laptop and go back to sleep when the head of customer success calls you in an absolute panic. Support tickets are skyrocketing because the main search page is completely blank. The business is bleeding $10,000 a minute, but your infrastructure is basically telling you everything is fine. Welcome to this explainer on Grafana and what senior engineers know that most developers really don't. We're going to break down exactly how the veterans survive production nightmares that junior engineers honestly don't even see coming.
Okay, let's unpack this. What I just described is known in the trenches as Incident 26. Your CPU is low and your error rates are 0, but the user is experiencing a catastrophic failure. The application isn't crashing gracefully, it's just returning 0 results. When the logs are empty and the dashboard is green, but the business is actively losing money, well, that is when your career as a senior engineer truly begins. You have to stop and ask yourself, why is the dashboard lying to me?
The short answer? You've fallen into what we call the observability gap. See, traditional monitoring is fantastic at catching known unknowns. The things you already expect might break, like a database running out of connections or a disk filling up. But modern distributed systems? They are infinitely more complex. A single request might traverse 15 different microservices, and this creates unknown unknowns, these emergent failure modes you've literally never imagined. Your infrastructure is perfectly healthy, but the actual business logic has completely failed.
There is a fundamental psychological shift in how top-tier engineers approach a failure like this. The junior approach is entirely reactive. They see a problem, they restart the Kubernetes pod, and they just kind of hope for the best. Or worse, they use the scream test, turning something off and waiting to see who screams. Yeah, that's a career-ending move in an enterprise environment. The senior approach, on the other hand, is systemic. Seniors ignore the initial noise, they look for the architectural flaw that allowed the failure to exist in the first place, and they trace what we call the semantic signal.
Which brings us to a core engineering tenet. Monitoring the plumbing is not the same as monitoring the water quality. You absolutely cannot just track whether an HTTP request returned a 200 success code. Returning a 200 OK with 0 search results? That's a massive failure to the user. We have to implement semantic monitoring. This means tracking actual business logic value, like search click-through rate or average items per cart. If your system processes thousands of orders a minute and suddenly that drops to 0, a senior engineer knows that alerting on the absence of that business value is way more critical than alerting on server CPU.
Now, modern tooling actually gives us the power to close that observability gap. The open-source Grafana LGTM stack handles this beautifully. You've got Loki handling your logs, Grafana providing the visualization, Tempo managing distributed traces, and Mimir's scaling your metrics. When you have an incident where the status code is 200 but the result count is 0, this stack allows you to seamlessly correlate that distributed trace right back to the exact infrastructure metric and log line. You stop guessing, and you start seeing the complete narrative of a request.
So the crucial point here is applying the right framework to all this data. You can't just measure everything arbitrarily. Senior engineers rely on these two battle-tested methodologies. The red method is for your request-driven services. You measure the rate of requests, the error percentage, and the duration, or latency. Then the use method is for your infrastructure. You measure resource utilization, saturation, which is how much work is queued up and waiting, and errors. Together, red and use cover the essential health signals of almost any distributed system out there.
Let's see how this builds into another massive production nightmare, the alert storm. It's 2:59 a.m. and your database CPU hits 100%. 10 seconds later, the order service fails. 20 seconds after that, the front-end alerts trigger. By 3 a.m., you have 450 unique PagerDuty notifications vibrating your phone right off the nightstand. You literally can't find the root cause because the signals are completely drowned out by the noise. The monitoring system has basically become a denial-of-service attack against your own engineering team. And the root cause here isn't just the database, it's a flat alerting hierarchy.
Here's the thing, the fix for an alert storm isn't just raising your alert thresholds. That just creates silent failures. The senior solution is implementing alert inhibition and grouping. A senior engineer configures the system to explicitly map dependencies. If a single outage triggers hundreds of alerts across the stack, the system should automatically group them and inhibit those downstream symptom alerts. Think about it. If the database is down, you page the on-call engineer once for the database, and you automatically mute the 400 alerts from the microservices that are simply complaining about the database being unreachable.
Okay, so you've set up your read and use metrics, you're tracking business value, and you've beautifully grouped your alerts. The system is perfectly observable. But wait a second. You just instrumented every microservice with thousands of custom tags? What is the hidden trade-off here? What's the real cost of hyper-observability? Take a second to really think about the infrastructure penalty of doing this.
You've just triggered a cardinality explosion. Every unique combination of a metric name and a label, like say attaching a specific user ID or a dynamic session token to a metric, creates a brand new time series. At high scale, this high cardinality data eats up massive amounts of memory. If you aren't careful, your observability database will literally cost more to run than the actual application compute resources. It's a classic trap. You have to be strategic. Senior engineers only instrument the absolutely most critical business pivot points, and they rely on traces and logs for the highly granular, high-cardinality debugging data.
And the reason we have to be so careful with scale is because of numbers like this: 30,000. In a contemporary hyperscale environment, like Uber, a single ride-hailing request from a user's phone might traverse 500 discrete microservices and initiate over 30,000 remote procedure calls, or RPCs. When one single request triggers 30,000 internal network calls, performance is no longer just about writing fast code. Performance becomes an emergent property of the entire distributed system. A 1 millisecond delay at the very bottom of the stack compounds into a massive user-facing timeout.
To survive at that kind of scale, you need incredibly practical backend architecture fixes. First up, eliminate the N+1 query problem through eager loading in your database calls. This is absolutely non-negotiable. Querying a database 100 times instead of twice will collapse your system under load. Second, utilize mechanical sympathy like the LMAX disruptor pattern, which uses lock-free ring buffers for ultra-low latency. Third, minimize your network tax by switching from bloated JSON over HTTP to compact binary formats like gRPC. And finally, remember that physics always wins. Fix the network path by co-locating chatty services in the exact same availability zone to physically reduce the distance your data has to travel.
Let's look at how systemic tuning actually plays out in the real world. A Tier 1 bank tuned Apache Kafka for ultra-low latency trading. And notice how they didn't just tweak one random setting. They tuned the producers to batch 32,000 records with a tiny 1 millisecond linger. They scaled the broker network threads up to 48 just to handle the queue times. And they optimized the consumers to pull 10,000 records per poll. They balanced the entire pipeline from end to end, relying heavily on specific observability metrics at each layer to prove their tuning was actually working.
And speaking of that pipeline, for Kafka, absolutely nothing is more important than consumer lag. This is the difference between the latest produced message and where your consumer is currently reading. If you are relying on end users to complain that their data is stale, you have already failed. Proactively monitoring that records lag max metric allows you to detect a consumer falling behind and scale up your partitions way before the business ever even notices a delay.
So here's the payoff. When you combine proper architecture with mature observability, when you track consumer lag, when you group your alerts, when you monitor semantic business logic, you achieve a massive 40 to 60% reduction in mean time to resolution, or MTTR. If downtime costs your business $500 a minute, cutting an hour-long outage down to 30 minutes saves you $15,000 instantly. The return on investment for building a proper observability stack like Grafana LGTM literally pays for itself in the very first major incident.
Okay, let's pivot and dive into the most counterintuitive secret of senior engineering: technical debt. When a junior developer joins a team, in their first year they might add 50,000 lines of code. They build APIs, utility functions, complex layers of abstractions, and everyone is impressed. Now, a senior developer joins that exact same team. In their first month, they delete 15,000 lines of code. They remove whole microservices, eliminate dependencies, and consolidate functions. The junior's graph looks like a mountain peak. The senior's looks like a valley. Guess which one the company actually values more?
There is a classic engineering adage for a reason. Senior developers don't write better code, they delete more of it. You see, every single line of code is a liability. It is not an asset. Every line can break, every line needs maintenance, and every single line adds cognitive load to the human brain trying to debug an incident at 3 a.m. The senior engineer knows that reducing that cognitive load and eliminating the surface area for bugs is infinitely more valuable than adding just-in-case functionality.
So how do you actually put this into practice? You follow the strategic deletion process. Step 1. Delete redundant code. Combine those 12 slightly different send notification functions into one solid function. Step 2. Remove unused features. That complex analytics dashboard nobody has opened in 2 years? Kill it. Step 3. Eliminate premature optimizations. You really don't need a complex Redis cache for a settings table that changes maybe once a month. And Step 4. Drop underutilized dependencies. If you're only using 5% of a massive NPM package, just write the 20 lines of code yourself and drop the dependency entirely.
I want to leave you with this final provocative thought. The absolute best code is the code that doesn't exist. The fastest way to ship features isn't adding functionality, it's actually removing the barriers that slow you down. So I challenge you, look at your architecture today, audit your dashboards, look at your code base. Next time you sit down to implement a brand new feature, ask yourself, what can I delete instead? Trust me, your future self, especially at 3 a.m. during an alert storm, will thank you.